Recording. Right. Now we're recording our second video, and I'm just going to jump straight into the setup for my laminar flow and make sure it's 2D double precision. Doesn't take too long to open up. Not responding. Hmm, Not good. Dog. It's cool. What's loading? I'll talk about why I chose things in certain values. So I wanted to make my Reynolds number, our critical Reynolds number is 500,000. I decided to choose 55 as my Reynolds number to have a decently size or pace, nothing but too slow, but nothing too quick to make sure it's perfect laminar flow. Because too slow wouldn't have really worked at first try five and it didn't work. But I'll jump right into what I've done. So it's the same mesh, same sketch. Make sure it's pressure based, absolute steady and planar. Go to models, select the laminar for my viscous model. Then I go to my materials, air, well, fluid air. So I made my density 1 and my viscosity 0.18. I was making it bigger and smaller, but this is the value that worked for me best. That solid aluminum doesn't change. Into our boundary conditions. So my in velocity, I think we chose, yep, puncture outlet 0. Everything else stays the same as my inviscid flow video. Thing to look at right there, reference values. Make sure this is set to inlet velocity and everything is set to what I want it to be. It didn't change anything. Simple and presto. Same thing as my inviscid flow. I will be changing that for my laminar or my turbulent flow though. Same thing over here I did before. My report definitions, my drag, and my coefficient. But person initialize, same thing. 25 initializations. So I'm gonna run my calculations. It's gonna be 1,000 iterations, same as before, and I'll get back to when it's done with the 1,000 iterations. But here we can see our drag force is loading in and our drag coefficients is, and here's our velocities and our, well, my X and Y velocities. Calculations took a while, but now we can go to report definitions. I'll click over here. We'll click wall. This is going to be a drag coefficient being recorded. And a drag coefficient of 1.36, which is a good drag coefficient for laminar flow at 55 Reynolds number. Usually you want 1.5 to 1.8, but for my calculations, this worked for my purpose. And we can check our force. Compute. 58. That's my drag force. We go to my plot. First, my graphs actually. Contours. Maybe my pressure contour, static pressure. You see our high pressure region and our low pressure region over here. Development of that. And here we have the change in pressure. Here, to display kind of our wake region. And the fixed wake region. No velocity over here. It was the minimal velocity and our velocity going over. And then the looping. Here's that. Plot. Here's my laminar flow plot. for the curve right there. Also check out velocity. And it's going to be zero because of no slip conditions. I'm not. Well, I didn't even go over my inlet velocity. This 10. I think is no slip condition. And nothing here either. Okay, no slip condition right here. And that should be all we can do. Our first fourth, yeah, forces. We can do we can jump. This will do our lift. We're gonna move on to our result. Okay. We can make the video a little longer. This close into a results. Oh, same thing in the results. I just made a streamline. Yeah, it was already streamline. You got a rodeo. You can change you anyways. There's the streamline. Kind of just appeared, but streamline I actually meant to do from symmetry fluent maybe 10,000. But then we can see the development of our streams. And we have no wake read. We have one more. Let's see what happens with velocity and speed. All right, 100%. Oh, whoa. Look at that. Wait, interesting. That's insane. It's a wake region if I've ever seen one. It's so cool. It's gotcha. Conclude the video for Laminar.